Welcome back to our geometry series. Today we are up to section 3.5 where we will be discussing altitudes and some bisector theorems. Here's our good friend triangle ABC again. I'm going to draw a line from B to a point X that we added on segment AC. We're going to stipulate that BX is perpendicular to AC, so it creates a right angle right at point X there. A segment is an altitude if and only if it is from a vertex of a triangle and perpendicular to the opposite side segment. So in this case, BX is the altitude. Like with the bisectors and medians, we can do them from any point. So from point C, we draw a line to its opposite side, AB, to point Y, such that it is perpendicular. And finally, we can see the third altitude here, AZ, from point A, connected at point Z, so that it's perpendicular to BC. Let's take a look at a slightly different triangle. Let's focus on point C. Let's try to draw the altitude from point C. Remember, it must be perpendicular to the AB segment, the segment that's opposite from point C. But no matter where we try to draw this thing and touch the segment, we can't find anything that would make a perpendicular angle. So how do we do this? Remember, it must be perpendicular to AB. So in this case, we have to extend AB to outside of the triangle. So here, point X, which is on the same line as AB, creates a segment CX. This is the perpendicular point, and this is the altitude from point C. It's a little weird being outside of the triangle, but this is how you would draw this particular altitude. Medians are always inside the triangle, but altitudes can exist outside the triangle. Let's look at point B. This one's pretty straightforward. It's a drop straight down to segment AC at point Y, such that BY is perpendicular to AC. So here's the altitude from point B. Let's take a look at point A. This is another case where we need to extend BC to create the altitude so that we have a perpendicular line from A to BC. So here's point Z, drawn in such a way that AZ is perpendicular to BC. This is the altitude from point A. What about a right triangle? Let's look at point B. The altitude from point B is AB, since segment AB is already perpendicular to AC. The same is true from point C. The altitude from point C is segment AC, since segment AC is already perpendicular to AB. And finally, we'll look at point A again. This one's a little more straightforward. It's a line from A to X, such that AX is perpendicular to BC. Let's jump over to the whiteboard and do some examples. Okay, let's just draw kind of random triangle like this. And we'll just give it some points, good old ABC. And let's draw some altitudes and kind of eyeball them. Let's start from B. So looking at B, we want to draw a line that comes down and is perpendicular to AC. So that's kind of here-ish. We'll call that X. And I'm just going to use a dotted line so it's not super busy. So BX loop is perpendicular, so that's an altitude. A, we have to get perpendicular. Again, I'm kind of eyeballing this. Something like that. And that's perpendicular. And we're going to call that Z because Y is going to be over here. And if I kind of eyeball it again, something like this. Again, 90 degrees. And here's Y. So there's the three altitudes of this triangle. Let's do one slightly differently. That's more of an obtuse triangle like this guy. Here we go. And we'll just call it ABC again because I'm lazy. And let's start with A because that one looks pretty straightforward. That's kind of here-ish. Whoop. So there we go. A to X. So now from point C, we need to draw a line that's perpendicular to AB. And again, if we try to do that inside here, it would be much less than 90 degrees. So we have to extend BA. And I'm just going to use a solid line, all right, such that we can go from C and come straight down to some perpendicular point here. Right about there, if I had to guess. Again, just kind of eyeballing it. Again, important part is that this is perpendicular. We'll just call this Y. I know you have to go from B to AC in such a way that we're perpendicular. It's already kind of flat to the table here. So I'm just going to extend this out to about here, not run into the other triangle. And this altitude is going to be more or less straight up and down, coming down to here. X, Y, and Z. Here we have a line with 2 points on it, A and B. I'm going to add 2 points, X and Y. Y is on the same line as A and B. I'm going to draw it such that segment XY is a perpendicular bisector of AB. So it's perpendicular, so we know the angle there at angle Y is 90, and we know that AY is congruent to BY. This leads us to Theorem 31. If a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. So looking at this, if a point, X, lies on the perpendicular bisector, XY, then that point, X, is equidistant from the endpoints of the segment. Likewise, if a point is equidistant from the endpoints of a segment, then it lies on the perpendicular bisector of a segment. Theorem 31 and 32 are kind of inverses of each other. Here we have line M. I'm going to put point X out here in space and connect it to line M at Y, where it's perpendicular. The distance from a point to a line is defined as the length of the perpendicular segment from the point to the line. So the distance from point X to line M is XY. Remember, we don't put a bar over XY. We're not talking about the segment. We're talking about the measurement of the segment. So XY is a numeric value. Here we have angle XAY. I'm going to draw ray AT as it's a bisector of XAY. Since it's a bisector, we know that the two angles that are created are congruent. So angle XAT is congruent to angle YAT. This leads us to Theorem 33. If a point lies on the bisector of an angle, like point T here, then the point is equidistant from the sides of the angle. So in this case, point T is equidistant from the side AX of the angle and the other side AY of the angle. Conversely is Theorem 34. If a point is equidistant from the sides of an angle, then the point lies on the bisector of the angle, which kind of makes sense. If it's right down the middle, it will be the same distance from either side of the angle. Let's go back to the whiteboard and do some quick examples. Okay, what we're going to do here is draw a couple of lines. It's not very straight, but you get the point. This will be a segment, R and S, and then just on the edge here, I'm going to draw a line like this, and this will be P, and this can be Q. And we're going to say that PQ, the line, is perpendicular bisector of RS. Alright, so now that we know that PQ is a perpendicular bisector of RS, what do we know about this figure? Well, let's start with the first one. It's perpendicular. So we know that all four of these angles will be 90. So let's just draw one box. So PQ, perpendicular to RS. Okay, that's a bisector of RS. So what it's doing is taking this segment, and bisecting it, cutting it in half. So although I drew this very poorly, this point, or this segment and this segment are congruent. We could call this, I don't know, point X right in the middle there. So we know that RX is congruent to xs. What else can we say about this? We've got point Q out here. And Q, we'll just say, Q is on a perpendicular bisector of RS, which we already know. So what can we say about that? It's on the perpendicular bisector. Therefore, it must be equidistant between these two. This is so because of Theorem 31, right, if a point lies on a perpendicular bisector of a segment, which it does, then the point is equidistant from the end points. So whatever this is this. So because of Theorem 31, we know that RQ, that's a terrible R, is congruent to SQ. And that's it for today. If you'd like to see more examples, stick around. Let's go back to drawing a triangle. Let's be on the screen, please. And we're going to make a nice isosceles tall triangle. I want to draw the altitudes of this triangle. And we'll give them some points and names and letters. So B seems to be the easiest to start with, right? Which we need to draw a line that comes down and is perpendicular to AC. Okay, what about from point C? How do we draw a line from here to here so that's perpendicular? Well, because this triangle is so tall and skinny, its altitude is right about here, right? And the same for A. It's going to be right along the bottom. So these altitudes are very short. Okay, we're going to do a little proof here. So let's draw a triangle, best that I can, something like this. And we're going to have S, T, M, and R. And we're going to say, given, still on the screen? Sort of on the screen. Triangle RST, the big one, has a median TM. So the TM is the median. We'll keep that in mind. We also know that TS is congruent to TR. Alright, so we get our nice little table going here, like this, with our statement and our reason. Oh, what we're trying to prove, we need to prove that angle S over here is congruent to angle R. Okay, first thing we do, let's write down our givens. Triangle RST has the median of TM. That's given. But what does that really mean? It means that TM is a median, so it cuts this thing in half. It bisects. It's finding the middle of SR. Let's write the rest of our given first. That TS is congruent to TR. So let's just write TS and TR. We know that much. And we know that SM is congruent to MR because that's the definition of a median. So SM is congruent to MR. And we're going to write one of those weird things that TM segment is congruent to TM. And that's just the reflexive property. Something is always congruent to itself. So now we have three sides of a triangle and three sides of a triangle. So we know now that triangle STM is congruent to triangle RTM because of the side theory. We've got three sides. And now we can say that angle S is congruent to angle R because the corresponding parts of congruent triangles are congruent. Yeah, that's right. And we did it. That's it for today. We'll see you next time.